What is capacitor? Capacitor is a passive element designed to store energy in its electric field. Capacitor consists of two conductor plates separated by an insulator or dielectric. In dielectric between them, basically there are two plates, and the dielectric is in between it. So, in the capacitor is equal to the capacitance. The charge stored in the capacitor plates, the conducting plates, is equal to the capacitance multiply the voltage across the capacitor, and the capacitance depends on the dielectric, the area of the plate, and the distance between the plates. We can say C is equals to epsilon A upon D. If we use the air, so we use epsilon naught. If we have some other material than air, we have E naught into ER. So if we have air, we can say this is epsilon naught. If we have another material, we have ER. So we can say that Q is equals to CV. So we have the charge. So if we want to calculate the current, and as we know that the current is the change of charge, and the change of charge per unit time is called current. So we have to differentiate this one. We place Q in this way. So we have CV. So as we know that C is a constant, so I is equal to C dV by dt. So this is the current flowing through the capacitor. So this means that when the change of voltage across the capacitor in a time, so it will have a current. It will allow the current go through. If the voltage didn't change, like in DC circuits, the voltage of the didn't change across the capacitor. So when voltage is not changing, so V is equals to 0. So I basically dV is equal to 0. So I also is 0 amps. So here we have V is equals to 1 upon, if we want to calculate the voltage of the capacitor using this equation, so we have 1 upon C integral minus infinity to T and I dt, and we have to add the initial voltage of the capacitor, initial at T equal to 0. We say that time infinity we calculate the, if we have infinity at the start, so we have equal to infinity. Mostly in practical, as we know that we have that defined limit of the time. We have initial time and final time. We can say T naught to T, and this is the voltage at T naught, and voltage at T naught is equals to the charge at T naught divided by capacitance. Capacitance is constant. So power is equals to VI, as we know that V is equals to I is equals to C dV by dt. So we can say CV dV by dt. And what is the energy stored by capacitor? Energy stored by capacitor is, we have the P dt. If we integrate the power with over the time, we have the energy. So we have C V dV by dt is P. C is a constant, we put it outside. So dt and dt is cancelled, so this remains dV. So we can say the C integral V dV, and we know that the V integral of V is V square upon 2. So we can say 1 upon 2 CV square. So the energy stored by the capacitor is half CV square. So we can also write in term of that, as you know that we have V Q is equals to CV. So if we want to put V, we can write Q upon C. If we put Q upon C here, so it becomes Q square upon C square, Q square upon C square, and when we put V, so Q square, so C square and C is cancelled, so we can say Q square over 2C becomes a energy, whichever formula, both formula can be used. So we know that this is very important things. The capacitor is in a DC is an open circuit. Open circuit means that the voltage across the capacitor is do not change. So dV is not changing, is fixed, and the current flowing through the capacitor is zero, because when the voltage is not changing, the capacitor is zero, and it works as a open circuit. So if the capacitor in a non-ideal condition, capacitor is resist abrupt change of voltage. The abrupt change in the voltage cannot change abruptly like in the diagram here. If you say this is a capacitor that can just at this point the capacitor is V volts, and then another at the same second, at the same time it becomes zero. So then it can be possible only if the current moves is infinity. This only possible if the current is infinity, and as you know that in practical condition we don't have infinite current, so we always have some time to discharge the voltage change. It cannot have an abrupt change in the voltage across the capacitor. So also we can say that in capacitor, if we have an ideal capacitor, that we don't have a leakage, whatever the voltage across the capacitor will remain same for the infinite time. But if we have the practical condition, as we discussed earlier, that we don't have a practical ideal capacitor, so what we have, the leakage resistance. So when we have leakage resistance, so capacitor do dissipate, but the resistance is very high. So this is why you can say that it's around 100 mega ohms, very high. So it can be neglected in practical calculations in some cases. So the question is that calculate the charge stored on 3 picofarad 10 to minus 12 capacitor with 20 volt across it. This is the charge. Calculate the charge. This is the capacitance, and we have the voltage. So we have Q equal to CV. So we have C, we have V, so we can directly calculate the Q. If you want to calculate the energy, so energy on the capacitor, so we know that capacitor energy is half CV square. We have C, we have V square, so we can say that capacitor can be calculated, the energy can be calculated half CV square, and 20 square is 400. Okay, so this is the answer, because the answer is in pico, so it remains still in pico. So the next example is that we have the capacitor of 5 microfarad, and the voltage across is the voltage is a function of time. Then we have to calculate the current, and we know that what is the current? Current is equals to C dV by dt. So we have to differentiate this equation. So when we differentiate this one, so tan cos, then the differential of cos is minus sine. The differential of cos is minus sine. So tan minus sine, so you can say C remains same. We have d upon dt. We have tan cos 6000 t. So we can say C into minus tan sine 6000 t. We have to integrate, we have to differentiate again the angle, so it is 6000. So we have minus comes from here. This is the capacitance 5 micro is 10 to minus 6000. This is this, tan remains tan sine 6000 t. So the answer is 0.3 sine 6000 t. We have another example. In this example, we have the capacitance. We have 2 microfarad, and we have the current is in terms of time. We have the current in terms of function of time. So we know that the initial voltage capacitor, we assume that the 0 is initial, and the 0 time is the voltage across the capacitor is 0, and we know that the voltage across the capacitor in terms of time, in terms of current, is 1 upon C integral the time from 0 to 3 I dt plus the initial voltage. So if we know the I, we know the I in term I is this one, and we know the T. So we calculate this ones in this way. So we have the capacitance 1 upon 2 micro. This is 6 is this equation, and this is a 10 minus 3 is the milliamps, as we have is the milliamps. So we use the 10 minus 3 is a milliamps. So it's a constant, so it becomes also outside. So we can say that 6 milli divide by 2 into 10 minus 6, and when we integrate it, so we have e power minus 3000 the t divide by this again with the differential of this one, so it becomes minus 3000. So we can calculate this 2, this is 2 3s are, this is cancelled, this is minus 3 remaining. So and we can say that this is 1000, this is also 1000. So this one minus 3, 10 raised to minus 3 multiplied 1000 becomes 1. So this all becomes 1, this all becomes 1. So we can say that minus e power minus 3000 t, and when we put the limit of 0 to t, so 0 to t, so we can say e minus 3000 t minus, sum is minus minus plus, e to the power 0, it becomes 1, so we have v minus 3000 t. So this is the volts across the capacitor. So next we have another example that we have the current determine the current through the 200 microfarad capacitor. We have the 2000 microfarad capacitor whose voltage we have given the voltage, and we tell that the voltage at different interval time we have different voltage. In the 0 to 1 second we have t, so it's a time function of time 0 to 0, and when we have time is 1, it becomes 50. So and 1 to 3 seconds, this is the equation, this is the graph that we have this equation. When we put the 1, so it becomes 50, and when we put 3 it becomes minus 50. So this is the equation, and when we put 2 it becomes 0. So we have 3 points, this point, we have this point, and we have this point. Just make a graph, it's linear graph. So we have, if we have 3 and 4, so we have, if we put 3 it becomes minus 50, and if we put the 4 it becomes 0. So if you want to calculate the current of this, we want to calculate the current, or so we have to calculate at each side. So current is the C dV by dt. I is equals to C dV by dt. So we have to differentiate this one. When we differentiate this one, so it just becomes a 50. So 50, and when we differentiate this one, this is constant. This becomes minus 50. This, when we differentiate this one, this becomes positive 50. This is 0. So this is 50, this is minus 50, this is 50. So just we have this one, and we have the capacitance is constant across the outside 200 microfarad. We can say 200 into 50 is into 10 raised to minus 6 is around 1000. This is into 10 raised to minus 6 is 1 2 3, because we want to store in milliamperes. So this becomes 10 milliamps, right? So this becomes 10 milliamps. So the first is 10 milliamps minus 10 milliamps, 10 milliamps. So 10 milliamps minus 10 milliamps. We can see that when the linearly change of voltage, the current is constant. Okay, this is the new finding for yours. So in the next case, we have to calculate obtain the energy stored in each capacitor. And we have the current source, we have the capacitor. So how to calculate the energy? First, as we told that the capacitor we consider as the open source. So this is, and this becomes open in DC circuit, then this is open. So then this is already we have the voltage across this one, which is V1. This is the voltage, or this is V2, as we have this voltages, and we have opened this. So the circuit becomes, this resistance is series with this resistance, and this is the parallel condition. So we can say that this is the current divider, and for the current, to calculate the I in current divider, as we know that we select the opposite side of the resistance. So if we have two resistance in current divider, R1, R2, this is the current source, and this is I. So if you want to calculate I1, so we have to use the R2 at the side. If you want to calculate I2, we have to use R1. So this is similarly we want to calculate I, which is on the right side, because this is open, this is disconnected, this is not available, this is disconnected. So this is, and this is series, this and this becomes series. So we can say the one, this we can make a simplified network. This is a simplified network. This one, we have this one, we have this one. So this is the one, we combine these two, 2 and 4 6, this combine 1. So we have 1 is 3 and 1 is 6. This is the 6 milliamps. We have to multiply with the I total. This is I total. So this is the current we have, 2 milliamps. Then energy stored in this of the capacitor. So we have to calculate it, the voltages across the capacitor. What is the voltage? What is the voltage V1? So we can say that the voltage V1 is equals to 2 kilo ohms into I. The current flowing from this resistance is I, as we know that this is open. So this, the current flowing from this is I. This is the 2 kilo ohms. So we have V is equals to IR. So 2 into multiply by I, so becomes, this is the V1, 4 volts. And what is the current going through this one? How to calculate the voltage across this network? How to calculate? So we have to calculate the current this one. So if you want to, if we calculate the voltage across these nodes, so which is equal to the voltage across V2. The voltage across this node equal to, because this is open, when it is open, the voltage across this point to this point is equal. Remember that when this is open, so this, the voltage across this point and this point is equal to the voltage across 4 kilo ohm resistance. So we have I 4000 I. So 4000 I is 2 milliamperes. This becomes 8 volts. So already we have 8 volts. We have the power. We know the formula of energy is equals to half C1 V1 square, and similarly we have half C2 V2 square. So we have the energy for W1 is 16 millijoules, and for the W2 is 128 millijoules.